Welcome to this explainer. Today, we're zooming in on the exact mechanism that's taking static robotic language models and turning them into highly capable, fully autonomous AI agents. We're talking about memory. It is absolutely the true evolutionary leap for artificial intelligence. So let's just dive right in.
Here's the roadmap for today's explainer. First, the forgetful language model. Second, types of AI memory. Third, hacking short-term context. Then, long-term memory and RAG. Fifth, the rise of agentic memory. And finally, context engineering and its limits.
All right, part one, the forgetful language model, and why standard LLMs literally can't remember your name.
So out of the box, large language models are what we call completely stateless. Basically, they are blank slates between calls. In practice, this means if you say, "Hi, I'm Martin," the LLM replies perfectly in that moment. But the second a new session starts and Martin asks, "What's my name?" the AI has absolutely no clue. It hasn't stored a single drop of historical information. If we want to build a true, helpful personal assistant, this forgetfulness is a massive roadblock we absolutely have to solve.
Moving to part two, types of AI memory, where we borrow from human psychology.
So how exactly do engineers solve this forgetfulness? Well, they look at the best blueprint we have, the human brain. They've essentially categorized AI memory into 4 human-inspired buckets. We've got working memory, that's the short-term chat history you're actively building right now. Then there's episodic memory, which is remembering specific past events and actions. Next is semantic memory, which covers external knowledge about the world, kind of like pulling facts from Wikipedia. And lastly, procedural memory, the underlying rules and learned behaviors that actually dictate how the AI operates.
Now, what's fascinating is that these 4 distinct memories don't just work in isolation. They function together within a single architecture. Think of it like this. When a query comes in, the LLM uses its procedural memory to literally know how to act. At the same time, it loads world facts from its semantic memory, checks its past actions from episodic memory, and keeps track of whatever you're currently talking about through working memory. It's an entire ecosystem, all working in total harmony.
Which brings us to part 3. Hacking short-term context, and the real limits of the context window.
You see, managing short-term memory isn't just magic. The AI relies on something called the context window. You can kind of think of this as the AI's RAM. It holds all the input tokens from you and the output tokens from the model. Early on in a conversation, you've got plenty of space, represented here by those unused white tokens. But, and this is absolutely crucial, this space is fundamentally a limited resource. Every single word you say, and every word the AI generates right back at you, eats up that space.
So, what happens when that space runs out? That's what we need to understand. When your conversation history hits the absolute maximum limit of that context window, the system physically cannot process anything more. The AI's output just gets abruptly clipped off mid-sentence, or worse, the whole thing just fails to output anything at all. It's like hitting a brick wall.
To prevent that massive crash, developers use 2 main hacks. The first one is trimming. This is basically a brute force chop, where we just delete the oldest messages in the chat to make room for the new ones. It works, sure, but you lose valuable information that way. The second, much more elegant solution is summarization. Here, we actually have the LLM read the past conversation and compress it into a tight, short summary. It saves that precious token space while still keeping the core context of the whole discussion intact.
All right, part 4, long-term memory and RAG. This is all about building an external brain.
Now, those short-term hacks are great for a quick chat, but what if an AI needs to read through a massive library of documents? For that, we use RAG, Retrieval-Augmented Generation. Honestly, it's the exact equivalent of plugging a massive external hard drive into the AI. The first stage here is ingestion. Real-world documents are passed through an embedding model, which literally transforms text into numerical dimensions. It mathematically maps the actual meaning of the text into coordinates inside a vector database, placing similar concepts physically closer together in this mathematical space. It's pretty mind-blowing.
Once we have that external brain built, the actual process of getting an answer, the inference, follows a really digestible 1, 2, 3, 4 rhythm. Step 1, we embed the user's query into numbers, just like the documents. Step 2, we search the database to retrieve the closest matching numerical items. Step 3, we augment, meaning we combine those retrieved items with the user's original prompt. And finally, step 4, the LLM generates the perfectly informed final answer. Seeing it in action, this creates a beautiful, seamless loop.
A user's query goes in, grabs the matching data points directly from that vector database, and neatly appends that retrieved context right into the prompt. Essentially, the LLM is being handed the exact cheat sheet it needs, just in the nick of time, to generate a highly accurate, informed answer.
Let's move on to part 5, the rise of agentic memory, or giving the AI the steering wheel. Okay, so what we just looked at was standard RAG, humans passively feeding the AI context. But right now, we're undergoing a massive paradigm shift, where the AI proactively hunts for its own memories. To make this happen, developers actually looked backwards to a historically proven human note-taking method called Zettelkasten. It's an old system based on atomicity, which just means keeping notes strictly to one single idea, and then linking them together to create a dense web of knowledge. While advanced agentic systems like AMEM do exactly this. The AI creates these atomic notes of its interactions, generates its own tags, and dynamically links its own memories together without human intervention.
And honestly, it gets even more advanced with bleeding-edge approaches like Search-O-One. Instead of retrieving all the data up front before answering, an agent is given specific tokens that allow it to literally pause, search an external database, retrieve the data, compress it, and then continue actively thinking. It iterates and refines its reasoning completely on the fly, entirely autonomously. It's like watching the AI actually think in real time.
Finally, part 6, context engineering. Because, as we'll see, more memory isn't always better.
We have all these amazing, complex ways to give AI vast amounts of memory now. But here's the catch. More memory isn't inherently better. You've probably heard the buzzword prompt engineering, right? Well, we've moved past that. We are now officially in the era of context engineering. We have to perfectly optimize the exact combination of the system prompt, the retrieved external context, the tool schemas, and the chat history. All of it flowing into the LLM at once. If you just stuff that context window full of random data, the AI gets overwhelmed. It gets completely confused. And the famous needle in a haystack test proves exactly why this strategic engineering is so vital. If we hide a single random fact, the needle, inside a massive block of text, the AI's retrieval accuracy drops drastically as that context gets longer. Look at this heat map. Even when modern AI models boast these massive million-token context windows, their accuracy degrades incredibly sharply when the haystack gets too large, especially if that specific fact is buried deep somewhere in the middle.
Which leaves us with this final, incredibly provocative question to chew on. If an AI can technically hold 1 million tokens in its memory today, is the future of artificial intelligence really about remembering more? Or is the true evolutionary leap going to be getting better at finding the needle in the haystack? I really hope this explainer sparked your curiosity and helped you visualize the incredible architecture behind AI memory. Keep learning, stay focused, and we'll catch you in the next one.